Got it. Turning off fan.
Now, if I could figure out how to clear the chat, that would actually help out a lot too. But that's okay. Oh, and I need to open up the lesson. We are farmers. All right, it's looking good. Okay. And yeah, it's behaving properly. So again, we're gonna go ahead and take this lecture to go ahead and finish out section 1.5. Um, yeah. Okay. So this is just a makeup lecture for the last one. Yeah. Anyway, okay. Like this. And so we this whole week we've been focusing on oh, and I need to show this like this. Oh, I'm glad that caused me to almost didn't show. So this week we've been focusing on transformation of functions. So we're going to go ahead and finish out this lecture, and then we can use the remaining class time. Uh, no, just use the chat. Use the chat for right now. I intentionally didn't allow you to unmute yourself because it helps me to focus. And then when there'll be a time when I'll allow you to unmute, but for right now, just use the chat to get my attention. That just kind of helps me to focus. Um, I will open it up with Zoom. Yeah. So again, with Zoom, the way Zoom goes, start with basically how you got in today. Start there first every day, and then if it's been about 5 or 10 minutes, if that's not letting you in or if it's not working, then you check your announcements because sometimes I'll send a different link. But for right, but here going forward, it looks like we can pretty much do this every day, right? Like I was testing out, okay, if I need to make a quick impromptu link, what does that take? So that was kind of like a trial run or whatever. But the way you got in today is more than likely how we're going to be getting in into the remainder of the semester. Also, I don't want you guys to stress about attendance, right? Do the best you can with attendance. If you want to be in the class and you're getting all your assignments submitted promptly and you want to finish, I'm not going to let the attendance stop you. It only really becomes an issue if we start racking up like four or more absences. But as long as you're in communication, I usually real light about that, and it's like, okay, I'll mark it as excuse or something of that nature. Um, yeah, okay, and yeah, it does kind of it can. And like last class, it was just me. Like I just overslept. That's all it was. Like I said, it was like 3:20. I think the class started at 3:50. I set an alarm for 3:40, maybe 3:35, something like that. And because I had like 30 minutes, I was like, okay, let me close my eyes. So I closed my eyes at like 3:20. I blinked and then I opened my eyes and it was like 4:40, and my alarms were going off. I don't know. It was weird. It was really weird. So I was just like, well, we just had to do a remote session that day. I mean, honestly, whatever we were gonna do that day, we're doing it now, and we really had an extra day kind of factored in there to to work problems. So we'll do the lecture right now, and if anybody just needs additional help with like working an example or something, we can schedule um, to just meet. Like I have our own meeting time or whatever. Okay, but yeah, but the what I'm pretty much doing is again just do the best you can with attendance, stay in communication. I'm not gonna be super strict. The attendance grade is just for records. I'm not gonna factor it into the grade. It only becomes an issue if we have like four or more absences. Then it's like, wait a minute, you can't be missing that many classes, right? But as long as you're in community, usually if you communicate with me, I usually mark you as excused if there's any kind of anything, and it's okay. It's not gonna hurt you. The main thing is submit our assignments via Pearson and Alex. Get those items submitted. Okay. So you kind of need both. Alex is going to be 10% of our grade. Yeah, it's okay to focus more on Pearson and do the best you can with Alex. Alex is just really there. You just everybody at a minimum needs to be completing about 25 topics per week, right? Do the best you can with that. Alex, the goal is for everybody by the end of the semester to be at the level of prep for college algebra or above. But Alex is only 10% of our grade. And the intent of Alex is just to fill in areas that we're deficient in, right? So do the best you can with Alex. My colleague sends me a weekly report. Um, you know, okay. But it's 10% of your grade, but majority of our grade does come from Pearson. Okay. All right. Again, I'm not gonna. The attendance is really for records. I know it's showing a grade. I'm not gonna factor that into your grade at all. That's just for my records, and it really only becomes an issue if we accumulate four or more absences. So if we continue our discussion on transformation of functions. I think where we left off, so we were supposed to start here last time, but where we left off on this notion of vertical stretching or compressing. So this notion of transformation of functions, to me, the ideas are simple, but it is kind of information overload. It's like a lot of information, and I don't really expect you to be proficient like that, but you just have to kind of push. And the level of being comfortable with it, the ease comes from repetition, right? The more we do it, then it'll sink in. So you just have to do high reps in a short amount of time in order to kind of get through it. That's kind of the name of the game. So with this one, we have this notion of vertical stretching or compressing. So if we multiply the outside of our basic function, maybe if I do it over here. If we multiply the outside of our basic function by a number larger than 1, then we get a vertical stretch. If we multiply the outside of our basic function by a number between 0 and 1, then we get what's called a vertical compression or vertical shrink, right? Those are the main points there. Okay? So again, don't worry about the grade with attendance. That's for records. The grades come from Pearson and Alex. That's pretty much it. Attendance only becomes an issue. Like I know it shows 50. That doesn't mean anything. It's just I just use attendance on whenever we meet for records. I don't factor that into the grade at all. The grade comes from Pearson and Alex, right? But attendance only becomes an issue if we start accumulating like 4 or 5 unexcused absences. Then it's like okay, you know. So similarly, if we can multiply the outside and it causes a either vertical stretch or compression, then this next part is what happens when we multiply the inside by a number, right? It says, let me read this one. It says, so the graph of f of b times x is obtained from the graph of f of x by multiplying the x coordinate of each point on the graph by 1 over b, right? So we're multiplying each x by 1 over b and leaving the y coordinate unchanged. So the result, essentially, if we multiply the inside by a number, if that number is between 0 and 1, it causes a horizontal stretch. If we multiply the inside by a number larger than 1, it causes a horizontal compression, right? To me, this is easier seen in action, and you just kind of have to work it until it sinks in. Because again, it's still following that notion that inside manipulations cause a horizontal change and are typically the reverse of our intuition, right? So all of these manipulations are inside our basic function, right? And so they want us to draw the final graph from here. So notice with this first one, we multiplied the inside by a number between 0 and 1. So your intuition might say, oh, that's going to cause a horizontal shrink because it's a small number, but actually it's going to be the reverse, right? It's going to cause a horizontal stretch by a factor of 2. Remember, we have to do 1 over b, right? 1 over b. Okay. So if we wanted to account for these transformations, when we graph it, what's somebody's favorite color? What color are you guys feeling right now? Anybody got a color they feeling? What color are you feeling? It's always red. What's the deal with that? I'm going to use pink because this one is already in red. I wanted a different color, but that's okay. So let's use pink. So if we multiply the inside by a half, that notice that that's between 0 and 1. That's actually going to cause a horizontal stretch by a factor of 2. So what that means is that the y values are going to stay the same, but now we multiply each x by 2 in order for it to work properly, right? So for instance, the y is going to stay as negative 1. I don't think we have anybody in the waiting room, and I think attendance is fine. So I think we're good there. Okay. So with the first one, again, y stays as negative 1, but if we multiply x by 2, the x goes from negative 2 to negative 4. So this is 1 point that we have on the graph. If, again, y stays as 0, but then x times 0 is 0 times 2 is still 0, so this point stays as is. Y stays as 3, and then the x gets double and becomes 2. Y stays as 0, the x gets double and becomes 4, right? And so then basically our new graph is going to be something like this, right? Like that. It still kind of clashes. I wanted something that popped in regards to the red, but yeah. So when we multiply the inside by a half, this is what a horizontal stretch by a factor of 2 or a factor of a half is going to look like, right? Basically, all the x's get double. And we see the result here. Okay. Let's do blue since that's the next color I see on the list. I'm not going to do black, so if somebody wants to give me a third one, we can use it. So then we'll do this one in blue, right? If we multiply the inside by 2, is that going to cause a horizontal stretch or horizontal shrink? If we multiply the inside by 2, does that cause a horizontal stretch or horizontal shrink? Right. See, so again, our intuition, because the 2 is large, we think it's going to stretch. Actually, it does the reverse, right? Remember, inside manipulations are the reverse of our intuition. Our intuition should say, oh, that's going to stretch by a factor of 2, but it's actually the reverse. So multiplying by a number larger than 1 on the inside is going to cause a horizontal shrink by a factor of a half. Basically, all the x's are going to get cut in half. So the y values stay the same. The y values stay the same. And now we cut our x's in half. So that x goes from -2 to -1. I think half of 0 is still 0. This x goes from 1 to a half, and the y value stays the same. This x goes from 2 to 1, and the y value stays the same. Then basically we get a graph. Let me do that a little bit better. Thank you. We get something like this. Why are you behaving this way? Okay, let's undo. Let's try it this way. Okay, that's better. And then from there to here. Yeah, that was good. Okay. So then multiplying the inside by a number larger than 1 causes a horizontal shrink. I think it's by a factor of a half. Basically, all the x's get cut in half. Okay, and we can see a digitally generated graph here. Keep in mind, we could always choose values of x, find the corresponding y. Most of the time. In this case, that would be a little bit of a challenge, but you know. So again, it says compress the graph horizontally by a factor of a half, right? So if we multiply the inside by a number larger than 1, that's going to cause a horizontal shrink by a factor of a half. Okay. Let's try the last one. Oh, this is gone. I need another color. I am going to do. Anybody got a color? Okay, I'm going to do purple. All right, so we'll do this one in purple. All right. Matter of fact, let's just add this to the favorites. Boom. Okay. So we'll do this one in purple. So it's actually the exact same graph as the previous, but now the x's go from positive to negative. So, for instance, the first point, the y value stayed the same, but then our x became what, 1? So instead of being -1, now our x goes to +1. I think the 0 still holds. This one went to a half, so now it's going to go to a -1/2, which is about here. And instead of going to 1, this one now goes to -1, right? And we get an image like this. It's doing that thing again. Okay. Let me undo. Let me go this way. It's a little bit better. Okay, this is simply it. All right, so it's basically the exact same graph as the previous one, but then we flipped horizontally over the y-axis, right? So if we multiply the inside by a negative, it flips it horizontally. Okay. Oh, my dog is gagging over there. She don't have to work that one out herself. I usually try to grab her and like hold her head over the toilet, so it's easy to clean up for everybody. But it's like it's whatever. It should be okay. Okay, we just have to work it out. You see the time? Anyway. All right. So that one again. That one was the same graph, but we flipped it horizontally. Okay. A little bit of an adventure. Let's see what's next. So we're asked to sketch the graph of this function. I think I actually want to graph this one, right? Let me get a copy. Ooh, lightheaded. Let's go like this. I don't need this. Go here. This. Copy. Okay. Looks good. And then we're gonna actually we can leave the view like this. Let's go paper. Get some graph paper going. Actually, let's try this one instead. Instead of graph paper, we're gonna do dotted paper. Okay. Let me see. So let me start by writing. Can I move this? Awesome. So let me start by writing getting a copy of the original, right? So we have this f of x equals, I'm going to rewrite it in the following way. We got negative 2 times x minus 1 squared plus 3, right? This is like the standard form of a quadratic. In this form, I can see that the vertex of the quadratic is going to be right 1 at 1 comma 3, right? So right 1 and up 3. So I'm going to focus on quadrant 1. So I'm going to go something like this. Actually, it's going to be a positive y direction. That looks good. This will be a positive x is going like this. Okay, that looks good. So again, this is positive y. This is positive x. So let's do like this. We'll go 1, 2, 3, 5, 6, 7, 8. I think we have way too much. We don't need that many. So I'm gonna go every 4. I think that'll be better. Okay, let me see. 1, 2, 3, 4. 5. I think that's enough. This is the origin. Okay. Okay. And this is going to be our 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 1, 2. Okay. Oops. And then actually, let me copy this and paste. Okay. And this one, let me delete that because I just want to keep that. I can use this blank graph in the future. Okay, and we're working here. Okay. All right. So now let's graph this, right? So I think it's a standard form of a quadratic, right? This says that the vertex occurs at 1 and then positive 3. So to the right 1 and up 3. Oh. So the vertex should be right 1 and up 3 is here, right? Notice that the leading coefficient is negative, so that means the parabola should open downward. And then we have this, vertical stretch by a factor of 2. So we can actually use the axis of symmetry, right? So we have, right here, we have this axis of symmetry. And let's go like this, style. We want it to be like this. And maybe, can we just want it spaced out? That's too much. Something like that, right? How about this one? Okay. So we have this axis of symmetry. So whenever we get a point on the left, we automatically get a point on the right, right? So let's do when x is 0, right? We're going to use the axis of symmetry to create this graph. So when x is 0, right? When x is 0, this is going to be negative 1. Negative 1 squared is positive 1. 1 times negative 2 is ultimately just going to be negative 2. Negative 2 plus 3 is going to be 1. So when x is 0, y is 1. So we have this point. But whenever we go 1 point to the left, we also have that same point to the right. All right. So if we go 1 to the left, we're at 1. That means if we go 1 to the right, we're also at a y value of 1. Okay. What happens if we do 3? That's going to be 2 squared is 4, negative 8. I think 3 goes off of our chart, right? So then we're just going to, let's say, something like this, right? It's a smooth curve connecting those points. This is about somewhere in between those. This is about here, and this needs to intersect there. Hang on, I gotta kind of keep playing until, okay, something like that, right? We'll get a graph similar to this. Let me see. It still is no good. Let's try this one. Put 3 there. What's that? 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then, I don't like it. Let me see. 1, 2, 3, 4, 5, 6. This one. 2, 4, 6. Closer. How about this one? Yeah, that's better. Anyway, that's the gist of it, right? We could have chosen another x value and been more precise, but that's the idea. So we started at the vertex. Again, in this form, it automatically tells us where the vertex is, right? So the vertex in this case is going to go to the right by 1 and then up by 3. It also says it's stretched vertically by a factor of 2. So basically the y values get doubled. And then we flipped it top to bottom. So this should be the final graph, right? Ooh. Okay. So then I'm going to go back to paper. And go back to this one. It was good. That's the gist of it. And then if we come this way. Oh, okay. So these are kind of walking you through the graph from each transformation, right? So the basic function here was a parabola, right? So we just had a parabola with the vertex at the origin. Then we subtracted 1 on the inside. That moved it to the right by 1. I'm not picking up right. I know, brother. Oh no, I'm sorry. I'm coming, guys. Oh, okay. So yeah. So if we look at the transformations in order, first we identified the basic function, right, with the vertex at the origin. Then we work our way from the inside to the out, right? So we subtracted a 1 on the inside. That moved it, again, even though negative 1 goes to the left, this actually moves it to the right by 1, right? Remember, the inside is the reverse of our intuition. So this one goes to the right by 1, right? The next one is we stretch vertically by a factor of 2, right? You see it here. Stretch vertically by a factor of 2. So basically the x values stay the same, but we multiply all the y values by 2. Then after the 2, we multiply the outside by a negative. So that flipped it vertically over the x-axis. So instead of opening up, now it's opening down. Okay. The last thing we did was we added 3 on the outside of our basic function. So that shifted the final graph up by 3. And we have this. Okay. Man, I love these sessions. Think about you like blink your eye and it's over. But we're almost there. We're gonna hit the mark. So with this example, yeah, of course. Anyway, sorry. It's the weekend. I struggle with Fridays. I'd be so scatterbrained. So yeah. Anyway, let's focus and bring this in. So it says for an artery with a radius capital R, the velocity v of the blood flow at a distance r, lowercase r, from the center of the artery is given by this, right? So this tells us the velocity of blood flowing through the artery based on the distance away from the artery, also based on the radius of the artery, right? Where c is a constant that's determined for a particular artery. So we write velocity, or the velocity based on the radius, or v of r, as this, right? Starting with the graph of y equals r squared, sketch the graph of this, given that the artery has a radius of 3 and our constant is 10 to the power of 4, right? So basically, they're just asking us to get a sense of this graph through using transformations. So the graph of this function, if we start with the basic function of r squared, right, that's going to be a parabola. Basically, it's just a parabola with a vertex at the origin, right? Let me think about it for a moment. So what I'm actually going to do here, to get it to look a little bit more like what we want, let me see, do I need to do that? If I do that, if I do that, I do that. Yeah. So what I'm going to do, I'm going to distribute this C first, right? If we distribute the C, then we'll get C capital R squared minus C lowercase r squared, right? So now I'm going to, and let's go ahead and plug in those values as well, right? So I'll just kind of continue here. It says that C is 10 to the 4, and so we're going to have 10 to the 4. Capital R is 3, so that's going to be 3 squared minus 10 to the 4 times r squared, right? And then just to kind of bring it on home, I know I could get some more space, but I think we can handle this. 9 times 10,000, that should be 90,000 minus 10,000 r squared, right? And this is the velocity based on the distance away from the center of the artery, right? So now, if we wanted to graph this based on transformations, we start with a parabola with the vertex at the origin. Notice this 10,000 is outside the basic function, right? So that means we're going to do a vertical stretch by a factor of 10,000, right? So we just multiply all the y's by 10,000. So we're going to have to scale this a bit. Then we multiply the outside of our basic function by a negative. So that's going to flip it top to bottom. Let me see. Alex. Yeah, there's no access code for our class. Everybody has their own individual Alex. Like whatever account you already have access to, you just keep working it, right? But it's not. There's no access code for Alex. Like for my class, I don't have a specific class for Alex. Alex is actually tailored for each individual student to try to help fill in your individual holes or gaps or deficiencies. Okay. Yeah. I only see the placement test on mine. Wherever you left off on Alex, that's where you should kind of keep going. So if you never took the placement exam, or if you did, if that's where you are, just work from there. Okay, let's kind of finish up this. Let me see. So again, we start with a parabola with the vertex at the origin. Then we stretch vertically by a factor of 10,000. Then we flip it vertically over the x-axis. So now it's opening downward. And then this is we added this 90,000. This is a positive 90,000 on the outside. So we're going to move it up by 90,000. All right. So let's kind of see. So we start with the parabola, stretch vertically by a factor of 10,000, flip over the x-axis, and then move it up by 90,000 units. And you see the graph here. Okay. Okay. So this says that the velocity of blood, so like this basically tells us the velocity based on the distance away from the center, right? So if we're in the center, then our velocity is at the highest, right? But then as we get further and further away from the center, our speed goes down. So the closer we get to the wall, the slower the blood moves, right? And then if it's on the wall, like all the way on the wall, then it's not moving at all, right? So it says the velocity of the blood decreases from the center of the artery to the artery wall, where it ceases to flow. The portions of the graph corresponding to negative values of R do not have any physical significance in this model, right? So that actually was the last of this section. I don't want to keep people for more than like 5 more minutes. Let me go ahead and give everyone a chance to unmute themselves. And if you wanted to ask questions, we can kind of get to the bottom of things. I know there was something like attendance and things of that nature. And I'm actually going to go ahead and stop streaming as well. Give me just a moment, gentlemen. I'll be right back.